Oh yeah, that's right. Who you gonna ask? You know the name. Who is it? That's right. Go on and bring it one more time. Who are you gonna ask? Now let's get this party started.
What up, everybody? Welcome to another episode of Let's Ask Paul. My name is Paul Abernathy, your host as always, and welcome to the podcast where I attempt to answer all of your pressing electrical code questions. Of course, you can send me something just in electrical in general if you like. I'll do my best to try to answer it for you. If I know the answer, I'll tell you. If I don't, I'll tell you I don't. But if you want to get involved in the Let's Ask Paul, you want to have your questions answered, you just always have these things you wanted to ask. Like if you're on the TikTok and people ask me to explain voltage drops and all this, dude, all of y'all, all you got to do is go over to paulabernathy.com. And over there, it's a very simple portal. You put your name in there, your email address, and you just type your question in and you click that submit button. And it comes to me, and you either would appear on an upcoming podcast like today, or I will even answer in an email because my goal is to get you the answer. That's what it's all about. So hopefully, if this is the first time you've ever been to Let's Ask Paul podcast, I don't know the number we're on now, but I'm thinking we're up in the upper 70s. I am not sure. Make sure you check it out. But if you want to listen to all of our previous Let's Ask Paul podcasts, all you got to do is go to paulabernathy.com. You can listen right there. In fact, there's a player built right into that website. You can do it from your phone. If you have downloaded our mobile app, now that is so cool because over on our website, you can download the mobile app. You don't have to be in our programs. You don't have to be in our Fast Tracks programs. I wish you were, but you don't have to be. You can get a lot out of our app. You can get access to our podcasts directly through the app. You can watch some videos directly through the app. You can go to the Sparky Hub right through the app, and it's free. It doesn't cost you anything. Now, if you are a Fast Track student or a monthly subscriber, you get more out of it. But if you just want to interact and get on the forum and ask questions and really just dig into understanding this code thing a little better, then get the app. Now, you can download the app from our website, electricalcodeacademy.com, .net, or .org, whatever. Up near the top, there's a little download button. Or you can just go to necchat.com. That's necchat.com. Download the app. Get it on your phone. Doesn't matter whether it's an Android or whether it's a iPhone, iOS, whatever. The app works either way. And so check that out because, it's a good way for you to stay in touch with like-minded individuals, but it also gets you access to some great features. And we also do the push notices from time to time. So if something I find out about, a code change in an area, something like that, then what I'll do is I'll push that code change or push something through to the members that way. Okay, so check that out. And of course, if you're trying to learn the National Electrical Code, there is no better way than our Fast Tracks program. So it is, without a doubt, the miracle of the code. Okay, we teach you what you need to know, and it also is great for companies who get all their folks on the same page. That's the beautiful thing. Now, our Fast Tracks are available in its color-coded format, by the way, before I get into today's episode. If you already are licensed and you want to deep dive and get a deeper understanding of residential, we have a Fast Tracks for that. That's a residential red program. If you want to learn commercial codes for commercial wiring, then you're going to do the Fast Tracks green. Now, if you're interested in industrial codes, which does get more heavily into motor aspects and things like that, then you're going to want the Fast Tracks blue. That's our industrial program. And of course, we have a purple, which is the grounding and bonding. That's called the Fast Tracks Purple. That's a deep dive into grounding and bonding. It's one of my favorite courses. So that's great for learning all those nuances in grounding and bonding. And of course, we have the Fast Tracks Yellow, and that is basically electrical theory, right? It's going to talk about parallel and series circuits. It's going to go into all of those type of things, resistors. It's going to deep dive into those things. so that you understand the fundamentals, magnetism, atomic structure. It just goes deep, and it's great for apprentices, but it's not so much codesy. Okay, it's more theory based, but that's the yellow program. And of course, we have what's called the orange, in case anybody wanted to ask. The orange is an all-encompassing. You get 4 courses of your choice. Usually people get the black, the red, and then they'll choose whether or not they want the green for commercial, and then the 4th one, they'll usually take grounding and bonding. Okay, and when you order it, you get the green, the black, the red, and the blue. And what you got to do is in the comments when you order, you get to substitute any 2 of them for what you want. So you could, instead of getting the blue and the blue and the green, maybe you want the black and the red. That's the exam prep and the residential. But you'd rather have the theory yellow, and you'd rather have the grounding and bonding purple. That's your choice. Okay, so you get to choose what you want, 4 of them. And you get access to it for 2 full years, okay? And the other big difference is those programs are certification programs. So when you finish those, you do get a certificate of completion, okay? You don't get that for the black because that's a fast track. That's exam preparation and general knowledge. But any of our red, green, blue, purple, all those type of things, you get a certificate of completion, okay? So anyway, that's it. That's the sales pitch I got for today. That's our fast track system. Check it out over on our website, electricalcodeacademy.com. And if you got any questions, just give us a holler. Okay, we're always here to try to answer questions for you. All right, so let's get into today's question that was submitted. That's what you came for, 6 minutes in or whatever it is. And you're thinking, Paul, are you going to ask your freaking question? All right, so I'm going to go to the first question. It says, Paul, love the podcast. Your podcast helped me pass my master's exam. That's what I'm talking about. On episode 75 about duplex receptacles, it seems backwards of what you would think. A 20 amp breaker can have a 15 amp duplex on it. If, for example, you had 2 devices plugged in and used 9 amps each, that would be 18 amperes on the duplex. Not enough to trip the breaker, which is 20 amp breaker, but more than the 15 amp rating of the device. That is true, but remember, as I said in episode 75, so those that haven't listened, to go back and listen to episode 75, if you remember, I told you that the guts of a duplex 15 is really the same as the 20. Now, I don't know why they charge you more. I guess I'm not sure, because there's technically it'd be more plastic with the 15 than it would the 20, right? Because they cut that little notch out. But at any rate, it is what it is. So that's what the code says, and I think you get it. One thing to keep in mind, and I don't know that I mentioned it in the other episode, is you do have to be aware of 210.23A1 and A2, and that is whether or not it's cord and plugged, not fixed in place, not exceeding 80% on any one of the receptacles. And when I say receptacles, the one contact device, not both receptacles on a duplex, right? Or not more than 50% fastened in place, but that's for the branch. So at any rate, don't ever forget that in your aspect. No, that has no play in this one here because it was a 20 amp rated device. So, a 20 amp rated breaker. All right, so it goes on to say, also, it was stated that a 20 amp duplex cannot be on a 15 amp breaker. That is absolutely correct. But the breaker would trip before the device rating would be exceeded. That is true. That is true. Now, you know that you can do this with a single simplex receptacle because 210.21A1 says that it has to equal to or exceed the rating of the branch circuit. So if it's a 15 amp branch circuit, I could put a 20 amp simplex receptacle. That's a single, one round receptacle on that and still be okay. I know it sounds backwards, doesn't it? But you can do that. Okay. You just cannot do that for a duplex, which equals 2 or more receptacles. That's what a duplex is. Hence the duplex. Yeah. It does sound confusing, but go over and listen, folks out there who are just tuning in. Go listen to episode 75 and it'd be a little bit cleaner. It seems like this individual fully understand what I discussed it because the real question here is at the end. And he says, I know you were just explaining the code, but didn't know if you knew the reasoning behind it. Thanks for everything. Well, sadly, in that scenario, I do not know the overall history of that, and I don't know that many people on Code Making Panel 2 probably know the history of that. So if anybody's out there listening that knows the history, the true history of why the device ratings on 210.21 A1 and A3 are the way they are, do me a favor, go to paulabernathy.com, send it in, and I will love to talk about it on an upcoming podcast. And I really don't know the history, except for the fact that I do know, again, that the duplexes, whether it's 15 or 20, they're exactly the same. So other than the faceplate configuration, other than that, they're exactly the same. So that makes sense. But the reason you can do it on a single simplex and not on a duplex, I don't know the whole history. Okay, it's just what the code says, and we just do what the code says. Okay, but I really don't. Sorry, I don't know the history. I'm not a historian. I tell that to people a lot. I'm not one of those historian type of code guys. If it's some kind of change that took place during when I was involved in code cycles, then yeah, I probably have been involved in it or heard a story or something or two about something. But a lot of that older stuff that's been around for decades, I'd have to research it. And you know what? It's a lot harder unless you know somebody that was around, because the public inputs, public comments, especially the way we do them today, you really can't learn a lot. You can learn some stuff, but you don't learn history. And when you go back and try to read some of the older stuff, you're okay researching it back till you probably get back to the 60s, and then it kind of, some of the way that they did their documentation was a bit wonky. So it is limited. So I'm not, but I am more than sure there's folks out there like Mr. Mark Odie who knows the history, or Jeff Sargent that knows the history. If they're listening and they want to reach out to me, I would love to know the full history of all that. Okay. So anyway, sorry. I can't give you the history. I can only give you the code, and I'm all about the code. So code is what it is. Sometimes we want to justify why we do something, but at the end of the day, you probably heard me say, just do it the way the code says it and just live with it. Hey, I also bet you that Fred Hartwell he's been around long enough. He probably knows the history as well, too. So Fred, if you're listening, I don't think you listen to podcasts, but you are. I'd love to have you send something in over on paulabernathy.com. Give me a little history, folks. I'm reaching out there to the listening community. Don't tell me what you think it is. If you actually do know out there, I would love for you to send it in to me. That would be awesome. Okay, let's go on and look at another question. All right, it says, my question is about dental office patient care rooms. I'm familiar with 517.13a, branch circuits in patient care spaces needed to be wires in metal raceways that qualify as an equipment grounded conductor. Okay. It doesn't always have to be raceways, though. We have like a smart hospital grade. We say hospital grade, or healthcare facility, HCF. It's really not a grade. That's receptacles that have grade. It's just a MC cable, for example, with redundancy, meaning the armor is actually designed to be used as an equipment ground, plus you have the insulated equipment ground inside for the redundancy, and that's what meets the requirements of 517.13a and b. So it doesn't always have to be a raceway, but you could meet it with a raceway. I could run an EMT, or I could run something and then have an insulated equipment ground inside of it. Yeah, so that's what he's saying, so I get that. And of course, he says, and 517.13b needs to have an insulated copper EGC. That's so correct. He says also, 517.16a isolated ground receptacle shall not be installed in patient care spaces. Okay. 6 foot from the sides and 7.5 feet above. Okay. I won't get into that because that's not really the question, but what does he say? Is there any specific layout that needs to be followed for receptacle location? Are smoke detectors, and those would probably be smoke alarms, because smoke detectors, okay, take that back. Those would be smoke detectors. What's in your house are smoke alarms. So this is a healthcare facility, so it will be a smoke detector. Kudos. Very good. Very good. But it says smoke detectors required to be in the patient care room. I don't know that one. I'll address the other one, but I don't know. I don't follow that anymore. That would be NFPA 72. That would be in the healthcare codes, NFPA 99. I don't really follow those, so I can't answer that question. I'm an electrical guy. And it says, and emergency lighting required in these spaces. Probably so for path of egress and things like that. So Article 700 is going to come into play. Your designer is probably going to design path of egress out of that building, and it's got to have a certain amount of foot candles and whatnot getting out and all this kind of good stuff. So I'm more than sure that if you're dealing with a healthcare facility like what you describe, then you're going to have egress lighting, and there's going to be designed that way. Probably going to have power packs up there, but at the end of the day, that's what the engineers do. That's their design. Okay. But if they don't design it and you're designing it, do me a favor. Make sure you check with the AHJ, the building official, because the building folks are usually the ones that are more anal about the path of egress and the lighting and everything like that might be necessary. But that's not really driven by the NEC. So I'll address the NEC part. The NEC part, which also isn't really addressed by the NEC, is there a specific location that needs to be followed for receptacle locations? Whether it's an operating room, whether it's a patient care facility, patient care spaces, or whatever it may be, as long as you have the number of receptacles that are required by the code, depending on that condition, then it doesn't matter where you place them. In fact, the placement is probably going to be where the administrator, the hospital administrator who understands their use and application, on where they're going to be laying their equipment out and things like that. So that's going to be more driven towards that part of it. And they're the ones that are going to be depicting where things go, right? That's something that they're going to be driving. Now, with the locations, you're describing a dental office. It's a little different, but if you're in patient bed location and you're talking about, doing, let's say, category 2, which is general care spaces or whatnot, they're going to give you some rules for patient bed location receptacles. And these are basically at the patient bed, like a headboard. And so you're going to get some rules that you have to follow. And so you're going to be in 517.18. You're going to be looking at B and that type of thing. But you'll also have critical care spaces, 517.19a, patient bed location. It tells you the branch circuits you have to have there. And obviously, if you have to have the circuits there, then that's where you're going to locate your receptacles. But in general, nobody other than that is telling you where they really need to be, okay? It's just a number. So, in the operating room, for example, if you were dealing with an operating room, by the way, in 517.19, and we were to look at C, it says the minimum number of and supply of operating room receptacles. Obviously, it says minimum 36 receptacles divided between at least 2 branch circuits, at least 12 receptacles, but no more than 24 shall be connected to either of the following. And it talks about the normal system branch, and then it talks about the critical branch circuit. But as far as the placement, that's really going to be largely dependent on what's in that operating room and how they design that operating room, or how things or equipment's planning on being laid out, right? There's no 6 foot, 12 foot if that's what you're asking. So usually these rooms are developed in a certain way. They're basically choreographed to their need. And so the administrator is going to work with a design professional, and they're going to know where the spacing is. Now, in your case, it sounds like you're talking about a dental office, and there's a chances are you're going to have none of that. There's no headboards, no patient care. So what you've got is like any other commercial building. Wherever they designate them, that's where you put them. Okay? And of course, they probably have some locations where they would prefer to have a receptacle for their needs, whoever owns the clinic or designing the clinic or whatever like that. So again, there is no spacing rule. You got the patient bed location rules, and typically at the headboard is where you'd have these branches, and obviously they would be supplying receptacles. That's about as close as you get to a spacing requirement. Other than that, around the walls, around the rooms, no. No rule on that, so you're good to go for that. Okay, let's go on and do another one, man. We're clicking right along here. We're only about 20 minutes in, so let's go on and do another one here. I've got another one that says, Paul, is installing a rain-tight connect on a Myers hub a violation of the NEC because the different threads. I've seen where electricians install a rain-tight connector on Myers hubs for outdoor equipment. Okay. Now, I explained this one over on my TikTok prior, very similar question to this. And so, again, this brings a lot of controversy with people, and it becomes a contentious topic. Myers hubs are just a brand, but there's a lot of people that make hubs. Bridgeport makes a similar hub. They're designed for rigid or intermediate metal conduit. Now, they have what's called NPT, okay? And those are tapered threads. And you have NPS, which are straight threads. Now, typically, a normal connector would be straight threads because you put a lock nut on it. That's a straight thread. The tapered is what's required in these hubs. So even when you see the hubs on top of a meter can and whatever, they typically are going to be tapered. And so you would have to use something with a tapered thread count, going into it. Now, I see people over in TikTok saying, I do it all the time, and I just fill it with caulk or whatever. You do you, boo. Well, you do whatever you want to do. But all I'm trying to tell you is that Myers hub, the brand, and I can't remember if they're made by Kraus-Heinz. I'm not sure who makes that. But Myers hubs are designed to receive tapered threads. So you cannot use it with straight threads. One, it won't seal right, and it won't hold out moisture, rain, condensation, wet, sprinklers. Anything that might throw water up on the thing could seep down into it. Now you're thinking, well, I'll just seal it with caulk, or I'll put silicone around it. You know what? It's still not right. And so people say, what are your options? Well, I don't know. You have to go search your options. There are tons of transition fittings that are out there. I don't know all the options, and I'm just telling you, it is what it is. Well, what's the harm? I'm not telling you it is a harm. I'm just telling you that it is listed, and a Myers hub is listed for a tapered thread, and it's not listed to go into something that would not accept tapered threads. Okay? So it's not listed for you to take something with straight threads into a tapered hub, okay, or vice versa. So it is what it is, okay? So with a Myers hub, you put that on top of your cabinet, and then the top of it typically screws in a rigid or intermediate conduit, right? And those are tapered. Then they screw down into it, it seals up, okay? So again, you have NPT and you have NPS, S being straight, T being tapered. You can Google it and get a great wiki describing all you would ever want to know about NPT and the threading and what it means. But you can also go look up the information about Myers hubs and, you can find out all the information that you'll ever want to get on the UL listing. I think it's DWTT, and if it's for grounding and bonding for services, KDER. Those are different things that you can go look up on the UL IQ and find that if you want. But at the end of the day, and in fact, you can even Google Myers Hub UL, and I believe there's an article out there that explains this. Okay. So I know they fit. I know you crank them in there. I know you put silicone in it. I know you do it. I know you're going to continue to do it. I'm just telling you, if an inspector ever turns it down because you brought a PVC TA into a Myers hub, those are not tapered. So they're usually straight. So it's going to ultimately end up not being sealed. And that's not what it was listed for. It was listed for rigid and intermediate. And another way you can verify that is just go to the manufacturer's website. Now, the same type of hubs, they're sold by Bridgeport, for example. You go look at it, it will tell you right there, point blank, right? Point blank, it'll say that this is for rigid or intermediate metal, threaded conduit. That's it. Doesn't say you can use it for plastic. Doesn't say you can use it for connectors with a straight. Okay. So again, if you don't believe me, go to ask the manufacturer. At the end of the day, they're the people that will know. And you just ask them and you'd be surprised what you find out. Okay. All right. So hopefully that answers your question. So no, a rain tight connector typically is not tapered thread. It's designed, and yes, it might have a grommet on it and everything, and it seals to the enclosure. And that's perfectly fine if you're bringing EMT or something into the enclosure. That's fine. But if you're going to be bringing something into the hub and the hub accepts taper only, then you have to use a tapered product into it, right? You have to use rigid or intermediate that's tapered. You can't bring in a connector that's straight. Hopefully I beat that to death enough that you know. I understand. I can hear it right now. There are people that are going to disagree with that. I get it. But I'm just telling you what the code says. And you do you, and you keep doing it. If you've been doing it for years and you've never had a problem, then you just keep doing you. I'm just telling you what the code says. Life isn't always easy. So I'm just letting you know. Okay, so this next question says, hey, Paul, love your podcast, and I love your new TikToks. Can you explain to me how to do voltage drop when what does he say? Can you please explain to me voltage drop when I increase the size of my hot conductors? What do I do with that equipment grounding conductor? Thanks in advance. Okay, great question. Good question to end on. So when we look at the National Electrical Code, you probably see me over on, if you follow me on TikTok. Again, it's not my favorite platform by far, okay? It is not, but I'm not going to lie, it has grown on me a little bit. It's the one platform that if you go over there and you spend any amount of time over there, you can't get it back, but two, the next thing you know, you just keep scrolling through these little 3-minute videos, and next thing you know, you've looked down and you spent 3 hours on freaking TikTok. And that's 3 hours of your life you ain't never getting back. It's not as bad as 3 hours of my podcast you'll never get back. But yeah, TikTok is like that. So when I did an explanation over there on voltage drop, I explained that voltage drop is not a requirement, all right? Except for in 2 places in the code. Sensitive electronic equipment, that's a requirement. And if you're not familiar with that, then you need to go look in the code. And sensitive electronic equipment is going to be found at Article 647. Now, again, this is very unique application. And if you look at it, you're going to see that 647.4D has a voltage drop requirement. Of course, it's 1.5% of the branch. And this is very unique for sensitive electronic equipment because it only deals with separately derived systems operating at 120 volts line to line and 60 volts to ground for sensitive electronic equipment. If that's the equipment you have going on and you find yourself in 647 for some reason, then remember for the branch, there is a voltage drop requirement. And basically 647.4D says that you shall not exceed 1.5% on that branch. Okay. I would only assume that it's because this is sensitive electronic equipment anyway, and it operates in a spectrum of the voltage that it needs to maintain at, and it really can't function properly when the voltage drops below a certain percentage. So here it's really making it be, driving it and nailing it down, right? Right, so that's that one. The only other location in here, now we're talking requirements for voltage drop, is when you're dealing with 695. And you all probably have heard me talk about that before. That is dealing with fire pumps. Now, with fire pumps, it's 695.7, and there's an A and a B. A is starting, B is running. These are critical for fire pumps. We have to make sure the voltage doesn't drop down to a certain point where that motor has a hard time running, because motors, they have this voltage width here, the highs and lows, that it is efficient. And if you drop down below the values of the motor, it has a hard time, especially with starting. So in this case, if you think about a fire pump, we're not trying to save the building. Yeah, that might be a byproduct. that it saves the building, stops a fire, localized or something like that. But that's not its goal. The goal is to come on, blow those sprinklers, put that water out, and give occupants of that building the best chance they can to get out of that building. I mean, that's what it's all about, right? We can replace buildings. We can't replace life. And so as long as you can try to maintain it enough and keep the fire at bay enough to buy people extra time to get out of that building, then you know what? That's what it's all about. And you know that we size fire pumps and everything that we do with fire pumps, we're really doing it to burn them up. We're not trying to protect them in any way. We're trying to burn them up, right? So it's one of those things that you have to understand, that voltage drop is a requirement in 695.7 A and B for fire pumps, and it is most certainly a requirement in 647 for sensitive electronic equipment. Okay. Other than that, the only real statement about voltage drop in the entire National Electrical Code is you have it under 210.19, where it makes a reference for voltage drop under A, the exception number 3. So 210.19A, exception number 3, kind of tells you that it's 3% to the farthest outlet, and it's 5% for the branch and feeder combined, right? So if you had 2% on the feeder, 3% on the branch, that would be ideal for this recommendation. But it's an informational note, right? It's not enforceable. It's just good info. Now, it's very efficient, and equipment's going to run efficiently if the voltage is within its operating range. When it starts falling out of that range, then equipment runs inefficient, generates more heat. And people say, isn't that a big deal then for a motor? Well, yeah, but the motors typically have overloads on them, so they're going to protect it from overloading due to heat. But again, it could prematurely cause motors to fail, and there's a reason it gives us a voltage range for this motor. So we like to stay within that. So when people ask, well, why don't you get that in the code? Well, for years, we've thought about pushing that in the code, especially the wire and cable industry, because we understand what can happen. But of course, we get too many people that'll see us and say, well, you're just doing it because you want people to increase their wire so that you sell more wire. Dude, I've heard it from everything. I have heard everybody on TikTok and Facebook and whatever say that everything that gets into the code is by manufacturers. Now, that might be the case in some things, like recently the gross expanded use of GFCIs everywhere, when there was never probably an issue there to begin with. And what am I talking about? I'm talking about the new 2023 that's going to require it for ranges and ovens and cooktops. I think that is overkill, but hey, it is what it is. But when it comes to voltage drop, we have to think about what we're trying to ask ourselves to do. So let's do for a second. Let's think about voltage drop. So if I'm going out to a load and I'm running a certain distance, and the voltage is going to drop, right? So when that voltage drops, if we apply voltage drop, then we're going to increase the size of those conductors, right? So it's like running water through a pipe. If you restrict it by squeezing it, you're going to have less flow. If you go bigger, then you have less resistance, okay? And as far as AC system, you have less impedance, which is made up of inductive reactance, inductive capacitive reactance, and you make it up of the actual resistance of the conductor. So, right? So you have inductive reactance, capacitive reactance, and you have pure resistance of the conductive material, okay? All of that makes up what we call impedance for AC. You with me? Well, with DC, it's really just the resistance, okay? That's what we're dealing with, okay? So for all intents and purposes, the same thing on both. It's a restriction to current flow, okay? But with the AC system, you have an expanding and collapsing magnetic field. It creates what's called counter EMF. This is why we want to run all the conductors together, close proximity, so we don't have this counter EMF and this rapidly expanding, collapsing magnetic field. And anyway, that's kind of what our theory program goes into. I'm just trying to give you the 30,000 foot view. But when we increase the size of those hot conductors, okay, the blacks, the reds, the blues, when we increase the size of those, remember, if we're lessening the resistance, we're lessening the impedance, it's going to allow a fault to take place somewhere in this line, and that fault current can be of a greater magnitude because it has less, it's lower impedance, right? It's a more conductive path for a crude way of explaining it. So when there is a fault, if you don't create a larger equipment grounding conductor, if there's a ground fault somewhere out on that system, that we just increase the size of the ungrounded hot conductors, then we're not going to clear an overcurrent device. In fact, it could cause that equipment ground to just burn up like a fuse. And so anytime that we increase the size of the hot conductors for voltage drop, or even if an engineer just tells us to increase the size of the hot conductors for whatever reason, then we have to do a little calculation. It's not hard, but we have to do a little calc to make sure that our equipment ground is going to be perfectly fine. Okay? And I'm going to walk you through it, and it's going to be a difficult one to do in a podcast. I get it, but I'm going to do my best because the question was asked, and people are going to say, well, why don't you do a video? Why don't you do a video? Well, I do, but you wouldn't be able to see them because all of my videos, you have to pay for them now. Okay? And I think I did do a video on that. It's available only over to our monthly subscribers. So if you're interested, go check it out. I think I explain equipment grounding conductors and sizing and what happens when we have to increase the size. But anyway, I'm going to try to do it in a podcast for you. Okay, so what we're going to do is we're going to paint a scenario. And we're going to show you how I logically would work my way through this. Okay, so hopefully you got your pen, your paper, and we're gonna walk our way through this. If we were to increase the size of the hot conductors because of voltage drop going, 500 feet, we want to make sure that we're not going to exceed that 3% voltage drop on that branch. Okay, it's a recommendation. It's not a code requirement, but for efficiency of operation of that circuit, if there's a luminaire at the end, it could glow dimmer because of the voltage drop. So there are considerations why we would do this, and I believe you should always take voltage drop into consideration, and it's not difficult once you have the concepts down. So we're going to do it. So let me paint the picture of what we've got. So the first thing I want you to do is I want you to go to 250.122 because we're going to be looking at equipment grounding conductors. So if you got your code books, got your scratch paper, or you're driving behind the wheel of a car, don't have a wreck, just listen until you get to your site, and then it'll be clear. You can always back it up and re-listen to it. You ready? All right, let's go to 250.122 real quick. All right, let me read the code to you because it's much easier for me to explain this as I read the code. So we're at 250.122. I want you to go to B. And of course, if you're listening to this podcast, you're probably thinking, well, dude, read it to me. I don't want to go get my code book. Okay. Well, it says increase in size. What does that mean? So obviously we're talking about the equipment grounding conductor because we're under 250.122. So that's equipment grounds. It says increase in size. It says if the ungrounded conductors are increased in size for any reason other than as required in 310.15b or 310.15c, wire type equipment grounding conductors, if installed, shall be increased in size proportional to the increase in circular mill area of the ungrounded conductors. So what does this mean? Let me break this down. So do you notice it says for any reason other than 310.15b and 310.15c? So if I have to increase the size of these hot conductors because of ambient temperature, in other words, because of the ambient temperature, I have to do a correction for that, then that means my conductor's bigger because of the issue of elevated ambient temperature above 86 degrees Fahrenheit, 30 degrees Celsius. Then I don't have to increase the size of the equipment ground because I just did it because of 310.15b. Now, if I have to increase the size of the conductors because the ampacity drops down because of number of current carrying conductors that exceed 3, and that's what 310.15c is. So say I have 6 current carrying conductors. You with me? And I have to, or even 8 current carrying conductors. Then I have to do an adjustment. And so the ampacity of that conductor will change based on its condition of use. And if you don't know how to do all that, we have a neat video called Derating Demystified, but you got to pay to watch it. I'm sorry, I don't do free stuff anymore other than these podcasts. So videos you got to pay for. I'm sorry. That's just, I'm a business and I have to run a business. And so if I'm going to educate you, you're going to have to pay a little bit. But that's your way of thanking us. $9.99 a month, you get access to everything. Okay, that's our monthly subscription. So anyway, so if you're increasing the size of the hot conductors because of the number of current carrying conductors or because of the elevated ambient temperature, then you do not have to increase the size of the equipment grounding conductor because the overcurrent device didn't change. You're just increasing the size of the conductors to compensate for that issue. Okay, now, if it does result in a bigger overcurrent device, then you still have to follow the rules under 250.122 depending on the size of that overcurrent device. But we're just saying in general, you don't just increase it, right? Now, notice that it said for any reason other than that. That means voltage drop is a reason. That means if the engineer just decides they want to increase the size for who knows why, then any of those conditions other than adjustment and correction purposes, then you would have to increase the size of the equipment ground, and you have to do so proportionally in that increase to the ungrounded conductors. And I'm going to show you how to do it, but I wanted you to understand the concepts of what we're talking about. So, key thing here. This section is with this, there's an exception as well, so we should probably look at the exception. The exception says equipment grounded conductors are permitted to be sized by a qualified person to provide an effective ground fault current path in accordance with 250.4, A5, or B4. Okay? So there is that exception in there. But I'm going to tell you that is typically something that would be done by an engineer. And it does say qualified persons. If you want to keep the smaller equipment ground, even though you increase the size of the HOTS, and something ever happens, boy, you better hope that you know how to do all that. Now, there are softwares out there that can help you. If you're doing metal raceways and using that as an equipment ground, you ain't got to do nothing anyway. But if you're using a wire type and you don't want to increase it because you think that the size is adequate, then, boy, you're the qualified person. You better surely know that it's going to be okay. Because if something happens and that doesn't trip and somebody gets hurt, and it'll be easy for somebody to look and see what size the conductors are and what size the circuit is and what size the ungrounded conductors are, and they're going to come after you. I ain't lying. So understanding how to do this is critical. Okay, but you do have an exception. If somebody is a qualified person that actually knows what they're doing, then they could get away with only sizing the equipment ground based on the overcurrent device, and regardless of the increased size of the hot conductors. But that's only under the exception, and that is only under the guise of a qualified person who knows what they're doing. Okay, and it's not that the electrician doesn't know what they're doing, but that's not our expertise. We don't go and do studies and tests or run it through programs to see what that would be. Okay? So, anyway, you want to do that, you do that, but that's the exception. So, we're not going to talk about the exception here. We're going to talk about what you have to learn to do. Okay? So, I'm going to give you a scenario. Now, remember, okay, what will trigger this increase? That's the key here. What's going to trigger it? All right? Number one, if those ungrounded hot conductors are increased in size because of voltage drop, then you're going to have to trigger the equipment grounded conductor size and see if it needs to be increased. All right? If the ungrounded conductors are increased in size for future growth or demand, or just because the engineer wants it, okay, then you're going to have to increase the size of the equipment grounded conductor, or at least compare to make sure it's still okay. Okay? All right. So let's kind of look at, I guess, let me give you an example about that. Just kind of throw one out there and let's see what it would be. Okay, so let's do this. So I have a 200 amp feeder is being installed because of a concern of voltage drop. the size of the ungrounded conductors is to be increased from 3/0, because we know that 3/0 is good for 200 amps copper under 31016, but it's being increased to 300 kc mil, okay, because of their concern for voltage drop. So it says, what size must the equipment grounded conductor be for this circuit? Well, there's some steps we have to go through. First thing we have to do is determine the required minimum size for the equipment grounded conductor, and we have to look at the different steps. So number one, we have to determine the ratio of increasing of the size of the ungrounded conductor. That's the first thing we're going to have to establish. Number two is determine the circular mill area of the wire type equipment grounded conductor that is required from table 250.122. Okay, so we have to see what would be required there. Next is we have to multiply the circular mill area of the required equipment grounded conductor. Okay, so what would be required for the circuit anyway, if you weren't doing the voltage drop, just what it would need to be anyway. So multiply the circular mill of the required equipment grounded conductor by the ratio that the ungrounded conductor is increased. So we have to do a little ratio calculation. All right, don't worry, I'll walk you through all this. And then, of course, we refer to Table 8 in Chapter 9. Select the next largest size equipment grounded conductor if the result is between the standard conductor sizes. If it falls in between, then you always round it up to the next available size. All right, so let's do this first. So the first thing we're going to do, and you don't have to do it, I'll follow you through this, is it's a 200 amp overcurrent device. So if you go to 250.122, the table, and you go down to 200, it says that a equipment grounded conductor for a 200 amp rated overcurrent device would be a 6 gauge copper. So I'm going to write this down. So 6 gauge, 6 AWG, EGC. You with me? Okay. Now, that's what we get for the table. Now, what is the circular mills, okay, of that 6? Where do you go? Okay, well, to get circular mills, we're going to go to Chapter 9, Table 8, right? That's where we're going to go. So you're going to go to Chapter 9, Table 8, and look at that. And what does that tell you? Chapter 9, Table 8 will tell you that that is 26,240 circular mills. Okay, so write that down. That is what the circular mills are for a 6 gauge. Okay? Now, while you're there, don't leave yet. We need to find out what the circular mills are for that 3/0 copper. Now, we know we're increasing it to a 300, so we know that the 300 kc mill is 300,000 circular mill. But what is the circular mill of a 3/0? Well, you're already there. Chapter 9, Table 8. What's a 3/0? Well, that is 167,800 circular mills. So far what you've written down is the circular mills of the 6 gauge, which would be the normal size equipment ground for a 200 amp device. So that would be 26,240. You wrote that down. And then while you were there, you went on and got the circular mills for that 3/0 because we need to create a ratio. So that was 167,800. Makes sense? Starting to make sense a little bit now? All right, so how do we get this ratio? Well, remember what we said? You take the new conductor that you want to run. In this case, was a 300 kc mill, and we're going to convert that into 300 times 1,000, so it's 300,000. Or the K means 1,000, so you don't need to do all that. So it's 300,000. You divide that into the original conductor that would have been designed for that 200 amps, which was that 3/0 at 167,800 circular mil. So let's go on and do that. So 300,000 divided into 167,800, and that is 1.788. That is your ratio of increase. See how simple that was? So you're basically taking the new conductor that you're going to because it's bigger, you're dividing it into the conductor you would have needed to actually do the job initially, which was a 3/0 because it's good for 200 amps. It'd be fine for that. And we're talking copper now. That'd be fine for that 200 amp device. But since we increased it to 300, you simply divide the 300 into the 167,800, which is, again, the circular mills of the 3/0. And that's how you get the ratio. So what do you do with that ratio? I know you're dying. You're saying, what do you do with that? Remember what we said earlier? You take the actual circular mil of the equipment grounding conductor that you would have needed for that normal 200 amp circuit, which we determined was a 6 gauge, which was 26,240, and you multiply that by that ratio. That's what it says in the requirements of 250.122b, okay? And so when you do that, you simply take the 6 gauge copper, which would have been the equipment ground for a 200 amp device, so 26,240, and you multiply that by 1.788, and that is 46,917 circular mils. Now, you're going to jump where? You're going to jump back into Chapter 9, Table 8, and I need to find a conductor with at least 46,917, and if one doesn't correspond, then I go to the next largest size. And I can promise you there isn't one that's going to be 46,917. So when you go to the book, let's go and look in the book. I got Chapter 9 right here. I'm going to go to Chapter 9, Table 8. I'm going to do it with you. And if you're riding in the car, don't do it. I'll do it. Relax. It's all good. If you go here, then what we're looking at is like, okay, I need something that's at least 46,917. Well, if you look at a 4, that's only 41,740. That's not going to work. The next one is 52,620. That's perfect. Okay, yeah, it's more than 46,917, but remember, it can't be less than 46,917. So I'm going to jump up. So what does this tell me? This tells me that my equipment grounding conductor got increased from a 6 gauge to a 3 gauge. So now I have 300 kc mils in there instead of 3/0 for the hot conductors. And instead of a 6 gauge for the equipment ground, I have to run a 3 gauge in there. And it's just that simple, folks. That is how you do it, and that's how you increase the ratio. All right? So those things are real important because when you're doing the raceway, of course, all of this takes up fill. So you have to do all this to make sure that your raceway is going to have enough room to be able to add all these conductors in there and not exceed the fill requirement. You need to make sure you meet the rules. But remember, if you're increasing the conductor size just because of adjustment and corrections or ambient temperatures in 310.15b or 310.15c, then that doesn't trigger this rule. But if it's increasing those hot conductors for any other reason, and voltage drop's the most popular one, then you're going to have to do this little ratio unless the exception applies. And unless you're a design engineer or somebody that has software that can actually calculate that out, I don't recommend you even looking at the exception. Just learn how to do the ratio and go and increase that equipment ground. Remember, the reason you're doing this is because you're putting bigger conductors going out. So if it has a ground fault condition, that the conductor for that return path for all that energy on that equipment ground doesn't burn up. It has to be increased in size to be able to handle that return current in order to clear the overcurrent device so we don't choke it out. Okay, so that's the whole reason we do all this. And it really is just that simple. So hopefully you got something out of that. It wasn't too complicated. I tried to do my best on a podcast, but that's it, guys. So hopefully you got something out of today's lesson. Again, almost an hour, but, hang in there with me. My podcasts aren't, they're usually long any freaking way. So anyway, till next time, folks, stay safe. God bless. And thanks to everybody who's following us and supporting us, all the monthly subscribers, the annual subscribers, all the Fast Tracks, and the new Fast Tracks Plus, whereas you get everything, even the online videos, everything is out now and it's available for those that really want to dig deep into the National Electrical Code, whether you're licensed or not. It's a great program. Till next time, folks, stay safe. God bless.
That's right. That's right. Go ahead. That's right. You're gonna ask Paul. Let's go. Kick it. Ask Paul. All right. Peace.